Investigating electric forces. The purpose of this lab was to investigate electric forces of two charges and be able to measure and quantify the charges to a pair of balloons. Our research question is, to what extent can we use Newton's second law and Coulomb's law in order to determine the magnitude of the electric charges? To perform this experiment, we used two balloons of equal size and weight and charged them on the same cloth at the same time for the same duration. Balloon 1 was fixed to a ruler and balloon 2 was left hanging on a string. The balloons were then brought together slowly until a noticeable repulsion occurred. This repulsion was recorded and analyzed using Tracker to solve for acceleration.
The models shown on this slide show how the balloon's energy changes in general. Both the bar chart and pie chart show 100% potential energy to start, then a 50-50 split between potential and kinetic, and then 100% kinetic. This models the balloon's motion while it accelerates. The free body diagram shows the electric force acting on balloon 2, gravity, and normal force were omitted due to the focus being on the net force due to charge.
Since we are assuming electric force is equal to the net force on balloon 2, we set the electric force equation equal to Newton's second law. This new equation was then rearranged so it is equal to the charge of the two balloons. An average acceleration and distance was used here. We assumed Q1 and Q2 had an equal charge because they were the same size and they were charged for the same amount of time. Therefore, to solve for charge of each individual balloon, we divided Q by 2.
The charge was calculated to be 7.99 times 10 to the negative 17th Coulomb for each balloon.
The number of electrons transferred into the balloon can be found through simple stoichiometry, shown here, and was found to be about 499. This is the acceleration versus time graph we made with our acceleration values from Tracker. As you can see, acceleration of balloon 2 is gradually decreasing as it moves away from the fixed balloon. The line of best fit is shown on this graph, but the value of acceleration that we used to solve for charge was an average.
From the data gathered through the Tracker software, we were able to determine the acceleration of the free-moving balloon. This acceleration was then used to calculate the force applied to the balloon, and from that force, charge was able to be derived using Coulomb's law. So in conclusion, the charge was calculated to be 7.9927 times 10 to the negative 17th coulombs, and the number of electrons transferred to the charged balloon was found to be 499. Again, the electrons are found through simple stoichiometry.
For our errors, the balloon's motion was not ideal, meaning that the balloon did not move in a linear pattern. This could lead to an inaccurate calculation of acceleration. Also, it was difficult to measure acceleration of the repelling charges. This is because the balloon moved microscopically, which is difficult to track, and could also account for an error in acceleration. Surroundings in the balloon were also charged, so the balloon was attracted to many surfaces. Therefore, it was difficult to distinguish whether the movement of the balloon was due to the repulsion of the other balloon or the attraction to another surface, which again would alter our acceleration calculations. The balloon may not have been exactly the same weight due to our scale that we used. Because the scale only contained two significant figures, the weights of the two balloons could have differed, which again would alter our calculations.